Hello, and welcome to this video on efficiency for GCSE Physics and Combined Physics, and don't forget to like and subscribe. In energy transfers within a system, not all of the energy is transferred usefully. Some of the energy is dissipated. This is spread out so it can no longer be usefully transferred. This energy is sometimes called wasted energy, and it often ends up in the thermal store of the surroundings, which causes the surroundings to heat up. A system is a single object or group of objects that we might be interested in, and a closed system is where the system is considered that no matter or energy can enter or leave. Within a closed system, even the wasted energy has to be accounted for. The value for the energy at the beginning has to be the same as the value at the end. There can be no net loss or gain. This can be shown using an energy diagram. The width of the arrows represents the amounts of energy. So we have 2000 joules input energy, we have 1400 joules as the useful output energy, and 600 joules, this is the wasted energy from the kettle, and this heats up the surroundings. Efficiency tells us how much energy or power has been usefully transferred compared with the total amount possible. If no energy is wasted, then all of the energy is usefully transferred, so the transfer is 100% efficient. This never happens. There's always some wasted energy. A device that gets close to 100% efficient is a room heater, as all heat going to the surroundings is doing the work of heating the room. Here we have two kettles. In these examples, this is the energy transferred every second. From these energy transfer diagrams, we can see that both kettles waste an amount of energy, 300 joules for the silver kettle and 150 joules for the purple one. But as different amounts of energy were transferred to the kettles, it's difficult to see which one is the most efficient. For this, we need to do a calculation. To find the efficiency of a device, you need to use an equation. Efficiency equals useful output energy transferred divided by total input energy transfer. And we use this equation when the question is about energy. Units for useful output energy and total energy input are joules, or they could be kilojoules. As long as they're the same unit, the efficiency calculation will work. Efficiency itself does not have units. When the question is framed in terms of power, we use this equation. Efficiency is useful power output divided by total power input. The units for useful power output and total power input are in watts, or they could be in kilowatts. As long as they're the same unit, the efficiency calculation will work, and as ever, efficiency does not have units. To find which of our kettles is the most efficient, we need to use the correct equation. As here the values are given in joules, then the energy-based efficiency equation is the one to use. So we look at our energy diagrams, and we have our energy inputs, our useful energy outputs, and our wasted energy. So efficiency is the useful output energy transfer divided by the total input energy transfer. And then we substitute our numbers for the silver kettle, and this gives us 306,000 divided by 360,000, which is 0.85 for our efficiency. And for our purple kettle, we have an efficiency of 243,000 divided by 270,000, which gives us an efficiency of 0.90. So our purple kettle is more efficient. We can also look at this problem in terms of power. As power is the energy transferred per second, if the kettles were on for 3 minutes, we can calculate the power using P equals E over T. For example, 360,000 joules was transferred in 3 minutes, which is 180 seconds. Then substituting into P equals E on T, we get 360,000 over 180, which gives us 2000 watts. On these energy diagrams, all of the energies from the previous slide have been converted into power. So now we can use our efficiency equation for power, which is useful power output over total power input. So for the silver kettle, it's 1,700 divided by 2,000, which gives us an efficiency of 0.85. And for our purple kettle, our efficiency is 1,350 divided by 1,500, which gives us an efficiency of 0.90. So we can see that the purple kettle has the same greater efficiency using the power route. But now we can also compare the kettle's power ratings and note that the silver kettle will boil the water faster as it is transferring more energy per second to the water. As no energy transfer is 100% efficient, all answers to the efficiency equation will be less than 1, i.e. 0 point something. If your answer is 1 or more, then you need to have another look at your calculation. A light bulb has a power rating of 60 watts and is used for 2 hours. The light bulb converts 10% of the electrical energy into light energy and the rest is wasted as heat. How much energy is wasted? So for this calculation, we need to look at power equals energy over time. 2 hours is given in our information. We need to convert that to seconds. So that's 2 multiplied by 60 to give us 7,200 seconds. Then we substitute our numbers into the equation, power equals energy over time, to give us 60 equals E, our energy, divided by 7,200. We then rearrange this equation to make E the subject, which gives us 60 multiplied by 7,200, and that gives us an answer of 432,000 joules. Now we need to look at the efficiency, use our efficiency equation, useful output energy transfer divided by total input energy transfer. 10% is 0.1 as a decimal. 0.1 being our efficiency is the useful output energy transfer divided by the total input, which we have just calculated as being 432,000. We need to rearrange this equation, and that gives us 0.1 multiplied by 432,000, and that gives us 43,200 joules. This is our useful output energy transfer. But the question wanted the amount of wasted energy, so we now need to calculate that. The total input energy transferred minus the useful output energy transfer gives us the wasted energy. So 432,000 minus 43,200 gives us our answer for wasted energy, which is 388,800 joules. An electric motor is used to lift a 50 kilogram load a height of 10 metres. The motor has an efficiency of 75% and operates with a power input of 2,000 watts. Calculate the time taken to lift the load. First, we need to use our efficiency equation, useful power output over total power input. 75% as decimal is 0.75. So 0.75 equals our useful power output over 2,000. Rearrange that and we get 0.75 multiplied by 2,000 gives us our useful power output. So we have our answer of useful power output of 1,500 watts. As this is the energy transferred every second, we still don't have our final answer. To get that, we need to work out how much energy is used to lift this particular load. To do that, we use potential energy. Gravitational potential energy equals mass times gravitational field strength times the height, which is EP equals 50 multiplied by 9.8 multiplied by 10, and that gives us 4,900 joules. Now we have our power rating, our useful power output for this particular motor, and we have the amount of energy needed for this particular lift of 50 kilogram load. We can now use power equals energy divided by time, substituting the numbers that we have calculated. That gives us 1,500 equals 4,900 over t, which is our unknown. Now we need to rearrange this for t. First of all, we need to multiply both sides by t. So we get 1,500 multiplied by t is 4,900. And then we can rearrange again so that we get t on its own, so that t is the subject, and that gives us 4,900 divided by 1,500, and we get our answer for time as being 3.27 seconds. To increase efficiency, several things can be done. Work done against friction can be reduced, and do this by using lubrication, for example oil in an engine. Efficiency can be improved by reducing thermal energy transfer, for example by using insulation. You can also improve efficiency by streamlining. Friction causes energy to be lost to the thermal store. If the appliance is a heater, then this energy is not wasted. But if the friction is between moving parts in a car engine, the wasted energy to the thermal store causes the engine to be less efficient. Lubricating the parts with oil reduces this friction so that less energy is dissipated to the thermal store of the surroundings. This means that more energy is usefully transferred and the efficiency is increased. The efficiency of heating a house can be increased by using insulation. The insulation prevents the transfer of energy to the thermal store of the surroundings. If less thermal energy is transferred out of the house, then less fuel needs to be used to keep the house warm. Less energy is dissipated, so the efficiency is increased. A streamlined car does less work against air resistance. This means a greater proportion of the chemical energy from the fuel can be transferred to the kinetic store of the car. This makes the car more efficient. And that's it for this video. Thank you so much for listening.